In this video, we are going to examine reaction mechanism and factors that affect reaction outcome. A reaction is a process in which a reactant is converted into a product. A reaction mechanism describes how the reaction proceeds from the reactants to products, and that includes the description of the electron flow and all the intermediates. So, mechanism also must account for the formation of any of the byproducts. And here is an example of reaction mechanism that you have seen before: addition of water to one butene, and that gives two alcohols, two butanol as the major product and one butanol as the byproduct or minor product. So you can see how mechanism shows using curved arrows electron flow, how it shows various reaction intermediates, how it shows a catalyst. So all those details are shown in the reaction mechanism. There is also one important principle that we apply when determining reaction mechanisms, and that's the principle of macroscopic reversibility. It states that reaction pathway is the same for both the forward and the reverse reaction, which means that if we know mechanism of forward reaction, we also know mechanism of reverse reaction, because reverse reaction will follow exactly the same pathway in the opposite order. So, for example, we can start on the right with 2-butanol, and we can carry out elimination or removal of molecule of water to end up with molecule of 1-butene. And the mechanism would simply work completely in reverse, going through exactly the same intermediates, same transition states, electron flow would be the same, everything would be the same, just in reverse. So that's the principle of macroscopic reversibility. Simplest mechanism involves single-step reaction. So a single-step reaction has no intermediates. That's called single-step reaction is also called concerted reaction. It has no intermediates. It only has reactants which go through transition state to give products. When it comes to kinetic and thermodynamic factors, we can identify 4 different basic cases of single-step reaction. In the first one, activation energy for this reaction is relatively low, which means the reaction is going to be fast. And products are lower in energy compared to reactants, which means that reaction is going to be exergonic. So this reaction is going to be both spontaneous and fast. If you want to carry out reaction, it will be an ideal case. This is kind of reaction we'd like to do. In the second example, we can also see that reaction is exergonic because products are lower in energy than reactants. So reaction is spontaneous, but activation energy is high. So this reaction is slow. So this is a little bit less favorable case, and in this case, we either have to use a catalyst or carry out reaction at higher temperature. In third case, we have an example where activation energy is low, so reaction is fast, but products are higher in energy compared to reactants. So reaction is endergonic, it's not spontaneous. Equilibrium is to the right, to the products. So this reaction will go very fast to establish equilibrium, but yield of products will be very low. Products will form in very small amount. So you may have to do some manipulations to shift equilibrium to the right, such as adding larger amount of reactants or removal of one of the products or something like that. And finally, fourth case is the least favorable. In this case, the activation energy is high, so reaction is very slow, and also thermodynamics is unfavorable. It's an endergonic reaction. Products are higher in energy than reactants. So this is kind of reaction we generally wouldn't like to carry out. We hope not to have to carry it out, but obviously we can lower activation energy by using a catalyst, or we can carry out reaction at higher temperature, but that still gives unfavorable equilibrium to deal with. A more complex case involves a two-step reaction. So in this first example, the first step is slow or rate determining step, labeled as RDS or rate determining step. So depending on the particular reaction conditions, you may have to supply energy such as heat, maybe light or ultraviolet radiation to the molecules of reactant R, so that they can be converted to intermediate I, so that they have sufficient energy of activation, delta G double dagger, so that they can be converted to intermediate I. So they go through rate determining step and are converted to intermediate I. Once the intermediate is formed, the main hurdle has been passed, because this high energy bump
has been overcome. This, you see this high activation energy. Now, from the intermediate, we have very low activation energy to go through second transition state. So low activation energy delta G2, delta G double dagger 2, to go through second step and finally to products. So the first step you can see is endothermic, and it's actually reversible step because intermediate can go either to products or to reactants. And energy for reverse step is not very high. Going from intermediate to reactant is relatively easy, relatively feasible, simply because activation energy needed for intermediate to reach transition state 1, transition state on the left, shown in yellow, is very low, and so it can go back to reactant. So first step will be reversible, while second is unlikely to be reversible. So first slow step is likely to be reversible, while second step is unlikely to be reversible because products would have quite a mountain to climb. They would have very high activation energy necessary to reach delta G double dagger 2, activation energy 2, to go back to intermediates. In the second example, and of course overall reaction is exergonic or favorable. So product is more stable than reactant. In the second example, first step is actually very fast step. And that first step, reactants have to overcome very low activation energy and be converted to intermediates. Obviously, this step is going to be reversible because both forward and reverse reaction are really fast. That's because activation energies either way are pretty low. But second step, in this case, is rate determining step because that's this high energy barrier. So intermediate now has to overcome this rate determining step, this high energy barrier, to be converted to product. So in this case, first step is going to be very fast, equilibrium step, while second step, again, is going to be non-equilibrium step, but it's going to be slow or rate determining step. So depending on relative magnitude of activation energies for the first and the second step, either first or second step is rate determining step. Usually it's the first step that is rate determining step, but sometimes it is the second. If first step is rate determining step, then as you will see from some mechanisms that we are going to study later, second step is frequently what we call product determining step. So if more than one product can be formed, it is the second step when it's going to be determined which product will be formed. So even though it's fast, it's still important because it ends up being product determining step. So distinguish between rate determining step and product determining step. And also for the second example, reaction is favorable, it's exergonic. As you can see, for net overall change in delta G, products are more stable than reactants. Organic reactions often can produce different products under different conditions. And the outcome of the reaction could be controlled either by stability of the product or the magnitude of the activation energy for formation of the products. So if it's determined or controlled by stability of the product, we call that thermodynamic control. If it's controlled by the magnitude of the activation energy, then we call that kinetic control. So when more than one product can result from a reaction, one with lowest energy content will be the most stable, and it will be favored under thermodynamic conditions. But for thermodynamic conditions, there has to be sufficient energy to overcome the activation barriers of all of the competing reactions. And also sufficient time has to be given for the reaction to reach equilibrium, so that most stable thermodynamically favored product can accumulate. So if we start with reactant, note that first this is not a two-step reaction. And you know that this is not a two-step reaction because reactant is given in the middle. And reaction goes either to the right or to the left, so two different competing pathways. Note that there is no arrow on the reaction axis, on the horizontal axis. So we have energy axis, vertical axis. We have a reactant in the middle, not on the left as in case of two-step reactions. And so reaction can go to the right or to the left. To the right, reaction has to overcome higher energy barrier, so higher activation energy barrier, and go to transition state 1. But once a reactant overcomes that energy barrier, it ends up giving product 1. And product 1 is obviously the most stable species on the energy diagram, the lowest energy species. Alternatively, and so you can see that delta H1 is the largest quantity here, or the larger of the two. Alternatively, transition state 2 is lower in energy. So reactant or reactants will proceed to form product 2 at much faster rate, because more molecules of reactant will have sufficient energy to overcome transition state 2 than transition state 1. So more of them will pass through transition state 2 than transition state 1 within unit of time, and will give product 2. So product 2 will form faster. So if we don't allow for equilibration, provided that these steps are reversible, if you don't allow for equilibration, then only product 2 will form, or will form predominantly. So we have to consider what are the reaction conditions. If reaction is carried out at high temperature, then molecules of reactant will have sufficient energy to overcome either transition state 1 or transition state 2. And so they will be going through both transition states and giving product 1 and product 2. But product 2 has much lower energy barrier to pass, to go back to transition state 2 to give back reactant. So reaction between reactant and product 2 is reversible, and they will be equilibrating. On the other hand, once reactant passes through transition state 1, even if that reaction could be reversible in theory, in practice it's probably not reversible, because product 1 has very high mountain to climb, very high energy to climb to reach transition state 1, and that's not practical, that's unlikely to happen. So product 1 is likely to accumulate. So while product 2 and reactant keep on going back and forth and equilibrating, any reactant that goes over transition state 1 will be converted to product 1 and will remain as product 1, will keep on accumulating. So product 1 will keep on accumulating. We call that thermodynamic sink. If we give reaction long enough time and temperature is sufficiently high, product 1 will be the only reaction product at the end. And we call such reaction thermodynamically controlled. So that means that high temperature and long reaction time is going to favor thermodynamic product or thermodynamic control of the reaction. On the other hand, if we carry out reaction at low temperature, then molecules of reactant could end up having just enough energy to overcome transition state 2, but not enough to overcome transition state 1. So only reaction to the left will occur to give product 2, simply because reactants don't have enough energy to go through transition state 1. And if on top of that we keep reaction time short, so that there is no time for equilibration, that product 2 and reactant cannot equilibrate, so that any molecules of reactant don't get opportunity just by chance to go over transition state 1, then product 2 will be the only reaction product. That would be kinetic product, and we call this reaction kinetically controlled. So short reaction times and low temperature favor formation of kinetic product. And of course you can see now as a comparison that delta H2 is much smaller compared to delta H1. That's an indication that P2 is less stable, product 2 is less stable than product 1. So in conclusion, to carry out reaction under kinetic control, we should keep reaction at low temperature and run it for short reaction time. On the other hand, if we want to carry out reaction under thermodynamic control, we should carry out reaction at high temperature and for long reaction time. You should keep in mind what is low temperature and high temperature, and short and long reaction times. That's actually relative, and that depends on particular reaction system. So sometimes low temperature may be minus 80 degrees Celsius, and another case, and high temperature may be 40 degrees Celsius. While in another reaction system, low temperature may be 120 degrees Celsius, and high temperature, for example, 200 degrees Celsius. And also short reaction times, sometimes it may be in seconds, in another case, short reaction time may be an hour. So short versus long could be seconds versus, let's say, half an hour, or in other cases, it could be one short reaction time, let's say a few hours, versus long reaction time, a few days. So those terms are relative. You should keep that in mind. And this completes our study of reaction mechanism and reaction control. Next, we are going to look at use of curved arrows, how to properly use curved arrows.